So I'm Karsten, and my partner is Robbie, and this is our final 357 PHYS project. This is a gyroscopically stabilized inclinometer, and Robbie's going to be detailing the operation and mechanics behind the circuit. But if you recall, our first two circuits had to deal with solar tracking, and this circuit grew out of a kind of further iteration. When we evaluated our Project 2 circuit, we realized that we pretty much brought that to the limit. We were tracking the sun across the sky and outputting its how well it did compared to like a stationary solar cell, and measuring the outputs. And so we already had computer control, and we had some data writing. So for this one, we really went for the intensive computer control. Our previous circuit made a really simple decision based on basically took the output of the circuit, and using the output of the circuit, it told the motor to go left or right. In this one, the computer is much more in control. In fact, the computer has complete control over the operation of the motors. So our whole project revolves around the computer trying to keep the output of this tip-tilt sensor to be level. And this sort of application obviously is geared towards anything where you need a stabilized platform pointing in one direction. And so that's kind of the application and impetus behind the whole circuit. So Robbie's going to show you the mechanics of the circuit, and then I'll come back and talk a little bit more about some of the details.
So here's a sneak peek of our final project here. We ended up using windowed comparators to do a centering type gyro where no matter how you hold the base of this, the top breadboard will seek to level itself via tip-tilt sensor. So if you tip it over like this, you can see the breadboard moving to level itself. And if you tip it like that, you can see both of those motors working to try and level the breadboard up straight, set it back down, and it levels itself pretty well. And so that is basically the overview of our circuit. And all of our circuit is basically ran through the lab jack, which goes over here to the lab view. And here's our input and output, and you can see the little lights light up if it's moving whichever direction, and then we have diagnostic voltages there. In terms of the code itself, we have a couple of case structures that determine whether or not the motor should move based off the windowed comparators, and then based off the voltage outputted by the tip-tilt sensor, we can decide which direction to move it. So we have the 4 voltages going into the lab jack, which are then fed into our code, and then we can keep track of those voltages for moving and leveling the breadboard on top, as well as keeping track of the voltages to just figure out how the tip-tilt sensor was moved, and then that's what we end up saving to the spreadsheet. So instead of having a common ground, which is usually the case for circuits, we ended up having a common positive lead. So we needed both 3.3 volts and 5 volts on our circuit. The 5 volts was to run the windowed comparators, and the 3.3 volts was to run the tip-tilt sensor. So as you can see from this diagram, instead of having the common ground down here, like I said, we had a common positive, which dropped down to the negative 3.3 and the negative 5 volts. So back to the front panel here, again, like I said, we have the LEDs that tell you which direction it's going and the voltages. And then finally, in terms of our output to a CSV or TSV file, if you hit stop here, it brings up the dialog box. And if you save the file, you can go ahead and open it. And in Excel here, it just gives you all the voltages, and we can end up converting that to how much the breadboard was tipped in both the X and Y directions.
So as Robbie showed you, the LabVIEW code outputs a nice tab delineated file here showing the voltages from our X and our Y axes of the tip-tilt sensor. The tip-tilt sensor, or inclinometer, that we were provided has a very nice linear relationship between the voltage and the angle. 90 degrees represents the axes being perpendicular with the z-axis, or the gravity axis. And as you can see, we can make a nice plot here of angle versus time. So as you see, our inclinometer starts out level, and then as we introduce perturbations to the mechanism, you can see how the motors recover and are able to keep it level. This is a variety of perturbations over a few seconds, so in both directions, just demonstrating how the motors work both when you're in the negative X and positive X and negative Y and positive Y directions. And finally it's leveled as we set it back down and the motor completely corrects. One thing to note here is the response time is good. It's on the order of a couple milliseconds. So this is definitely a very feasible and useful circuit, as well as interesting. So Robbie showed you the mechanics of the circuit and how it works. I'd like to talk a little bit more about our LabVIEW code, because this is really where we made a lot of progress since the last project, and where it really evolved and became much more complicated, as well as where we learned quite a bit. So the LabVIEW code is comprised of some nested case structures, and the whole concept of using the case structures and the nesting is really what allows this circuit to function well. As Robbie described, we're comparing the comparator as well as the actual raw voltages from the tip tilt sensor, and then making decisions based on which way the motors drive. As you can see, we can change here. This is for the case when the comparator tells our circuit that it's level on one axis. Of course, we don't need to move the motor, so nothing happens. And then nested within that, based on the actual voltage, we can change whether the motor is going to move left or right, and that has the other case structure. And then this would be a duplicate for the other axis. So these case structures and this is where I learned a lot personally, was thinking of LabVIEW, going from the graphical to more of a traditional coding and how that works. And the case structures represent like an if statement, and that was a really powerful tool for me personally to be able to, once I made that connection, I was able to write this code very quickly and get exactly the result I wanted. And being able to interface the computer with the LabVIEW code, with the LabJack and the circuit, and put that all together in a package that was small and light enough to fit on our gyroscopically stabilized platform, that was the significant development from Project 2. And the tip tilt sensor chip was instrumental. It's really the impetus behind this whole project, and I think I feel good about what we've accomplished here. It represents a lot of learning. I obviously couldn't do this at the beginning of this quarter, and pretty happy that I was able to get all the way here. So Robbie's going to share his observations. This is it for me for this quarter, and it's been a good time.
Before and after learning we had of the project was that we started out with our sun tracking circuit that you might remember from Project 1 that we ended up developing on for Project 2, had windowed comparators and a lot of logic in it. And from those that start, we ended up using the windowed comparator idea to do this tip tilt sensor. And the main learning curve was that with the windowed comparators, it was really easy if we were running them for voltages around the center of the voltage that we wanted in the window. But as I just mentioned, for this circuit, since we had it centered around 1 volt, which was closer to a low voltage since it was running off between 0 and 5, we were having a lot of trouble getting the window to work correctly. So once we adjusted the voltages as I indicated, the window comparator started working just fine. So that was one of the things that we learned about as we were going through the process. Another thing that I learned about that was just a dumb mistake is making sure that you declare the port on the NXT, because if you don't, you will sit there and bang your head against the wall for half an hour trying to figure out why the motor isn't stopping when you expect it to. And so windowed comparators are finicky at low voltages, and since the tip tilt sensor outputs such a low voltage, around 1 volt, we had to adjust that. And then always double check your LabVIEW code for the constants that should be declared, but that you may not have explicitly declared.